Everyone for coming today. Welcome to our annual COLA lecture. This is 2025. And so we're having this lecture here at the University of Bristol. And this lecture is named after Professor Kola. It was a Vice Chancellor here at the University of Bristol. And quite a big name in elasticity. I mean, I'm an elastician, so I know like he has a special place in my heart. So this is actually Jonathan's domain. So you should do this introduction, but it's not here tonight. So I will say something about COLA. I will go quickly through COLA. So it was aerodynamics. He worked in aerodynamics department in NPL in the 1930s. He worked on propellers with Glauert, that we all know, and Goldstein as well. Were popular people back in time. His work was on tail flutter, rudder flutter, and all sorts of flutters with Duncan, another very famous and important guy in elasticity. His principal achievements was magic theory and his application in general dynamics. And specifically, University of Bristol, he was the first to take the chair for St. George White Chair, sponsored by Bristol Aircraft Company, to set up the aeronautics department. And then he was very famous for the COLA triangle, which is the triangle that every elastician knows about the introduction of aerodynamic, inertial, and elastic forces. He was the first academic president to the Royal Aero Society, which we represent today. And then he was Vice Chancellor for University of Bristol. So this lecture, as we said, has been running for a few years now. I think this is the 10th lecture that we had. Like you can see like very important names across the board. And then today we are actually hosting Professor Benjamin Woods. I have some bio to read, or nothing here. So Dr. Benjamin Wood is a professor of aerospace structures at the University of Bristol and EPSRC Early Career Fellow. He has earned his PhD in 2012 from the University of Maryland in rotorcraft, blade active flap systems, while also working on a wide range of industry projects. He was instrumental in development of the world record-breaking Gamera human-powered helicopter, and he moved to the UK for a morphing aircraft postdoc in 2012. And he started his lectureship at University of Bristol in 2015. He has led a number of government and industry-funded projects, including the EU-funded Shape Adaptive Blades for rotorcraft efficiency. SABRE? Oh, that's good. Program. I'll leave the stage to you, Ben. And
thank you all very much for your time. I do very much hope that at the end of this you feel like it was time well spent. Basically, my job tonight is just to take you through a lot of the research projects I've been working on since my time here at Bristol. I would like to say, though, just to segue over from Collar, two things really quickly. So it was really a genuine honor when Jonathan asked me to do this lecture, because I actually remember very clearly 2015 when I came to watch him give the lecture. So I don't remember what he talked about, but I do remember this feeling that this is something nice, this idea of both recognizing the history of someone very important in our institution and in our field, but also just as an excuse to kind of come together and talk about what we do more publicly. So since 2015, a good solid decade ago, to me, the Collar lecture has been something just genuinely quite nice. And so as a result, I'm very happy to be here. The other thing that I'll say, because we're here, is this idea of the triangle, of course. So the triangle of aeroelasticity is an incredibly important part of how we think about Collar's work. It's an incredibly useful way to think about the physics of a very complex problem that we have in aeroelasticity, but it's also something that shows up a lot in my work. So I don't think I will ever come anywhere close to matching this list of achievements in front of you, but hey, at least we both like triangles. So I got that going for me. So with that, let me go ahead and bring up the slides I've got here. My talk tonight is called Shaping a Sustainable Future, and I mean that very literally. So everything that I'm going to talk to you about tonight is about geometry and the role that geometry can play if we're clever, if we're good, at helping us make a more sustainable future for ourselves and maybe be a little bit less awful to this incredibly beautiful planet that we are really good at destroying. So with that cheery start, I wanted to give you a little bit of a prelude, a little bit of a incredibly self-indulgent trip through my sort of history as a human being, as it were. And for me, that starts in the woods. So Woods is my last name, but it's also very much a huge part of who I was growing up. So I grew up in a very rural part of the state of Maryland on the east coast of the USA, right next to Washington, D.C. And my mom was a single mother. She worked in Washington, D.C., so I had a lot of afternoons home from school running around in the woods in our house. And it was really sort of where I felt comfortable and sort of happy and where I felt who I was. But there was a little bit of a transition, let's say. So as I approached my teenage years, I got sort of distracted and drawn in to the shiny, sexy world of aerospace engineering and airplanes. I was maybe a little bit, believe it or not, this incredibly suave man standing in front of you tonight was actually a slightly nerdy teenager. So I spent a lot of time obsessing over details of shiny World War II aircraft. The Mustang, of course, because I'm American, although I think today I would put a picture of the Spitfire instead. Anyway, the point of this is that as I sort of embraced that part of who I was and what I liked, I really kind of got into this idea of technology as this incredible, beautiful thing that can make real change in the world, and that maybe we can make new things that no one's ever done, and that was really exciting. And for me, it was exciting sort of because it was shiny, right? Because it was something different and new. And the point I'm trying to get to here is that I've really realized in the last few years, and okay, maybe I'm sort of halfway through my midlife crisis at this point, which is you'll be happy to hear is going very well. I've started to realize that part of me and how I approached engineering and what I liked about it, I don't really like as much anymore. I think that as a society, we have a really weird and unhealthy fixation on this idea that technology is the answer to everything, that the problems that we've created for ourselves and for the planet from previously developed technologies can only be solved, right, by new amazing technologies of AI or whatever else. And that just doesn't seem to be working for us. So in these last few years, I've really found myself maybe trying to get back a little bit more towards that little kid running around in the woods. And for me, I think this is just a picture of a pen that I made. It's definitely just me bragging because I made my own pen. But it's also, it kind of encapsulates where I'm at right now. So everything that you'll see tonight kind of mirrors this journey I've been on. And I think where I'm trying to get to with that sort of picture on the bottom right is some sort of balance between what's good and natural. And wood is a really good example of that as a material. And what's sort of shiny and nice and new and exciting with, in this case, a bit of brass that I've made into a pen. So apologies, a very self-indulgent introduction. And it's actually only one of two sort of self-indulgent introductions. And this is the second one. So this is, I promise, much more relevant. So if I were to try to show you a single picture that is my career in a nutshell, it would be this little acorn. And this is a stupid joke, right? Because this is my career in a nutshell. But there's actually a little bit of a story here. So when I was in 5th grade in geometry class, so that's sort of the US equivalent of year 6, I had a teacher, my geometry teacher, who at the time I didn't really have maybe a lot of respect for. He was just a boring old man teaching geometry, and he had a really bad tendency to just sort of throw in really quite corny jokes that didn't really ever land to us little teenagers. But unfortunately, I realized over time that there's something in what he taught me, literally, but also in who he was that I've kind of grown into myself. So this is actually a literal joke. So in 5th grade, my geometry teacher one time told me, what did the acorn say when he grew up? Gee, I'm a tree. Right? Which is a horrible joke. It's not even remotely funny, right? What does a tree have to do with the concept of geometry? It's not, it doesn't even, the punchline doesn't work. but I realized actually it's a little bit too on point because maybe I'm that acorn, right? And I've grown up into a tree or something. But the beautiful thing about this is that joke clearly stuck with me and ended up sort of accidentally like representing everything that I think I am, or that I think I care about, because geometry, it turns out, is actually pretty cool, and you could do a lot with it. So with that, let's talk about the actual talk and stop talking about myself quite so much. So the goal here is to see what we can do as engineers, as people trying to be as clever as we can to help solve some of these fundamental problems that we have on our planet. And I would like to make the case tonight, and I'll show you hopefully lots of examples that you find compelling, that, hang on, let me hide this really quick. You gotta see the punchlines. I hope to make the case tonight that geometry is an incredibly powerful tool in our fight to be less horrible. And in particular, I would argue there's sort of three ways to think about this. So if we want to make a more sustainable future for ourselves, well, the structures that we build, both as sort of traditional structures that we think of in terms of buildings, but of course also in an aerospace context, things like airplane wings, airplane fuselages, structures in the widest possible sense. If we want those to be sustainable, then we need to be a little bit more clever about how we approach that. And I think there's sort of three particular approaches I would sort of champion. The first being that we want to make our structures with less material, right? So we want to use less material, use it better, make that structure more efficient, make the the amount of fuel that airplane burns less, make the amount of CO2 that's going into the concrete to make our buildings less, etc. I would also argue that it's really important that we think about the fact that a lot of the structures that we build, again, be they sort of static or transportation type, or even wind turbines, etc., they very often have widely different operating conditions that they have to perform in over time. And geometry, again, can be an incredibly effective tool here, because the design of any particular structure for any particular job always has a very direct and strong impact on the shape of that structure. And the point I would like to put forward is that if we can create structures that can change their shape in real time to adapt to those changing conditions, then maybe we can make them more efficient. And the third point, which will come in towards the end of the talk tonight, is about natural materials. So maybe we can use natural materials as replacement for the highly extractive materials that our entire built world is made from today, that take incredible amounts of energy to produce, and then have all sorts of concerns about recyclability, et cetera. Wouldn't it be fantastic if we could replace those with more naturally derived, more sustainable materials? Well, that sounds great, but the very simple reality is that in general, natural materials are substantially worse. They have significantly lower performance. And so the argument again is, what can we do with geometry to make up for that? How can we use geometry to sort of offset those material deficits? So these are sort of the overall topics or framing I want to talk through tonight. And just to give you a little bit of heads up what's coming. This is the entire talk tonight. There's 9 different research topics, concepts, ideas, whatever you want to call them, that I'll go through. I have to apologize. There's kind of a lot here, so I will be doing more of a supersonic flying over of these topics than any sort of in-depth discussion. I'll show lots of pretty pictures, say a few things. Really, it's just to kind of show the breadth of ideas. Everything here is published and you can look at in more detail through papers, et cetera. Roughly speaking, though, the overall talk splits into 2 different categories. So in the first instance, I'm going to talk through my work on morphine aircraft. So that, again, as I sort of alluded to a few minutes ago, aircraft that can change their geometry in real time to optimize their performance, reduce fuel burn, et cetera. The second half of the talk, roughly, we'll be talking about Raptor trusses. Raptor trusses are a manufacturing technology that I came up with quite some years ago to allow us to build truss structures that are structurally efficient while still being really quick and cheap to make. So that's what's coming. I do have to start, again, with a little bit of a disclosure. So as an academic, as a professor, you may not be too surprised to learn that I don't actually do that much real work in my job. I don't actually get to do so much of the research anymore. So it's incredibly important that I just laid on the table, that everything that you see here, well, not everything, but a lot of it was done by other people, specifically PhD students, master's students, and research associates that I've had over the years. I've been incredibly lucky in who's come along and trusted their years of their life to me. I just want to reiterate again that what you see here is really more my ideas maybe, and then all their hard work. So with all of that multi-stage initialization of this talk done, let's go through. Let's start talking about some technology, some actual ideas. Let's look at some pretty pictures and have some idea of hopefully what I've been working on all these years. So I think it's quite fitting that I start by telling you about the fishbone active camber concept. So when I first came to the UK in 2012, I came to work for a professor at Swansea University, Professor Mike Friswell. He was actually also one of those Sir George White chairs here at Bristol before Jonathan. But he was incredibly kind to me. He basically gave me free rein on what I researched. And I had this sort of thing in my back pocket that I'd been thinking about during my PhD, but never got a chance to play with. And so I just went with that. And that was this concept. And it's the fishbone active camber because the point of it is to be able to change the geometry of an airfoil, specifically the amount of camber in that airfoil, as a way to directly control the amount of lift generated by that airfoil and therefore by that wing. Now the fundamental idea here, and you'll see it in most of the morphing work I've done, is the idea of compliance, flexibility, of making structures that can change their shape, not in discrete, rigid ways like we have already on every single airplane that flies with our elevators and our ailerons, et cetera. Those are all rigid changes in shape. We want to do it with compliance. We want to do it smoothly and uniformly and create things like you see in the video on the bottom left, where we change that camber in a really nice, smooth way. And that's not just because it looks cooler. That really is about, first and foremost, aerodynamics. We have shown, and you can see on the bottom right, very significant improvement in the aerodynamic performance of control surfaces when we use a fishback instead of a flat. And there's a lot of stuff here, and I'll talk about even more, but the key result on this page is the difference in the two lines on the bottom right. So in this case, we're looking at how efficient our airfoil is performing. So we talk about that in terms of our lift to drag ratio, where we want lift, but we don't want drag. So we want a high number for our lift to drag ratio. And we're looking at that as a function of our lift coefficient. So how hard we're working in the air, how much lift that airfoil is generating. And these two lines are a direct comparison between the fishback and the flat. And you can see that especially as we start to get into larger lift coefficients, so especially when we really start using that control surface, there's a huge improvement in our lift to drag ratio. And that is directly and explicitly coming from the fact that we're changing that shape much more smoothly and uniformly. And I should add as well that these are wind tunnel results. So that makes them slightly more believable. So based on that sort of really promising initial performance of the fishback, we've actually done quite a bit of different types of activity with it, a lot of different research. It's fundamentally really quite a complex problem because we are doing this in a compliant way. We have flexibility, so we can't just assume that when the shape changes, we know what'll happen. The actual shape that's created in any particular situation is a really complex balance between the structure, the actuation, and all of the aerodynamic forces and pressures are acting on it. So we have to use somewhat sophisticated analysis methods like fluid structure interaction in order to actually be able to predict what's happening. So there's a little bit of a other side of the sword when we get into this field because it does require a reasonable level of sophistication how we look at things. Having said that, we've developed a lot of tools and analysis methods. We've looked at the actuation side of things. We've got a tendon-driven actuation system, which is explicitly inspired by how our own bodies work when we move our muscles and antagonistic joints around our skeleton. It's a similar concept, so there's a lot to do with developing that tendon system, looking at the actuation side of it. We've done a lot of work on the aerodynamics as well, of course, with from low fidelity to medium fidelity to high fidelity methods. Another fun little thing along the way is this other related concept called MELD, which is a morphine elastically lofted transition. It's sort of a three-dimensional version of a fishback that allows you to have a variation in that camber along the span. There's some really fun geometry inside of that. I don't really have time to dig on it, but that's worth a Google on ResearchGate if you're interested. There's some fun geometry going on there. Now, I will say, genuinely, as nothing more than a brag, that I recently had to put together a case for promotion to professor, which happily went through. But as part of that, I had to sell what I've done. And so I started Googling around, and it turns out that actually this concept has been looked at by 24 other institutions all over the world. And then even happier still, the first person to show up tonight came from Southampton, and he said he came up because he is working on the fishback at Southampton as well. So that means 25 institutions, so keep them coming. Anyway, let's keep moving. Another related concept. So fishback is about changing camber. That's a really effective way to control the amount of lift that an airfoil generates. But there's a lot of other ways that we might want to change the shape of the wing that aren't quite so simple. One of the fundamental issues is that if we ever want to change the area of a wing, then we're going to need a material that can smoothly and flexibly change its shape. Now, this is really the ultimate core issue that's plagued all of morphine aircraft research from the very beginning. And I'm not claiming that I've solved it, but we do, here at Bristol, we've developed an alternative, again, geometry that allows us to tackle this problem with morphine skins in a slightly different way. And I think the key thing to get across here is that if you imagine the top of a wing, and maybe let's just say for the sake of argument, that you wanted that wing to get longer and shorter in order to change its span, in order to change its flight performance, you would need a structure that underneath those very high levels of aerodynamic load that you would have flying at, whatever, Mach 0.8, you need a structure that can get longer and shorter without bending out of plane. Right? You need to really control that out of plane displacement. You need high stiffness out of plane, but low stiffness in plane. And that's an anisotropy problem. You need a material or a structure that has very different stiffnesses in different directions. And that's what this is. So the Gator concept is geometrically anisotropic thermoplastic rubber morphine skins. Okay, you could probably see I was trying a little bit hard to get to Gator on that acronym. It's probably not my smoothest one ever. But the basic idea here is that we're using, again, geometry to create a structure, and there's one right here, where we have a sandwich panel, where sandwich panels in general are a really nice way to make something stiff out of plane. But we've done a trick. The core that's inside this sandwich panel, which you can see on the figure there, is actually what we call a cellular solid. So it's not continuous material, it's an architected geometry. And as you can see in the icon in the upper right, it's been specifically designed so that you can extend it as you need to extend the span of your wing, for example, in a manner where the core structure is able to bend. You have these really thin bending ligaments, which you're not pulling on directly, which would be very stiff. Instead, you're bending them. And that's a really nice way to keep your in-plane stiffness low. And as I mentioned already, we can use the sandwich panel structure with a flexible rubber skin to give us a nice balance of a higher out of plane. So this concept is working out pretty well. I've had a PhD student finish up on it. We've done some nice demonstrators. So there's an example here of a wind tunnel model of the fishback that uses this concept. And we're now looking at it on a bigger scale. But basically, the trick here, again, is to use geometry plus these flexible materials to give us a better balance of what we're trying to achieve. Now, this is our current work with the Gator skin. So there's a large ongoing project here at Bristol called DAWS2. I've got a tiny little bit of it where we're looking at using those Gator panels, that flexible skin panel, to solve a problem that's come out of a really interesting and sort of really prescient concept that Airbus is now looking at. And that concept is called the semi-aeroelastic hinge. So some of you may know that already. It's been a very sort of active bit of research, both here at Bristol, which before my time it actually originated here at Bristol, and it's since sort of gone to Airbus and it's being looked at very seriously there, including plans to actually flight test it in the next year or so. But the semi-elastic hinge has a little bit of a problem because the basic concept is that you take the very tip of the wing and you allow it to rotate. You allow it to bend out of the way of any oncoming gusts that would otherwise potentially break that wing. So there's some really clever geometry tricks going on with that concept itself already. But one issue that's created by it is that there's a gap. There's a hinge mechanism that you're putting outboard, and you can sort of see, you can see here in this flying small scale model, and you can sort of see in the larger renderings that this hinge needs to be covered up so it doesn't add too much drag, but unfortunately, it's actually angled to the airflow. There's a geometry trick going on with the basic concept that requires that hinge line to be angled. The result of which is that any sort of normal mechanical fairing that you might put over it ends up actually quite draggy because it's misaligned with the flow. So the basic idea of our work on that project is to use these compliance-based mechanisms, this gator concept, to cover that hinge with a structure that can smoothly deform while taking that load. And you can see some initial prototypes here, and there's 2 RAs working on that now, with another related piece of work looking at the aerodynamic optimization of the shape of that hinge, the fairing rather, in order to minimize its drag. So we've got some really fun CFD optimization work going on with that. So staying on the semi-elastic hinge, but moving in a slightly different direction. A concept that I've been playing with for a few years. I don't have a good name for it yet, apologies, so we'll just call it a 2-stage torsional stiffness for now. I'll come up with an acronym at some point, or acronym, as I say here, because you don't just have the acronym, of course, you have to make up a name that gives you a good acronym. It's a very delicate science. It's a black art. I spent a lot of time thinking about it and worrying about it. But anyway, so back to that semi-elastic hinge concept. One of the other realities of how that concept works is that in normal everyday operation, when you're just cruising around, you would love for that wingtip to be level. You would almost love for that device to not even be there. You just want it to look like a normal airplane wing. Up until the point where a gust hits it, and you need that device to move out of the way to reduce the load generated to make sure you don't have any issues with failure of the wing. Now, the current approach to doing that is rather active and mechanical. So, they're looking at various devices that can keep that wing locked in place, and then they detect a gust and they release it as an active process. The concept that I'm looking at is a way to replace that active device with something that's purely passive. So literally springs and levers and maybe a bit of cable. Where the fundamental idea, in the simplest possible way, is that if you could make a spring, a torsional spring, that's really stiff in its initial working range, then that would be really good at keeping that wing as level as possible in normal flight. But if it was always that stiff, then when the wing started to bend out of the way of the gust, you would end up transmitting a lot of torque, a lot of load that would then load up your wing and kind of defeat the purpose of the semi-elastic hinge in the first place. So the trick then would be to be able to come up with something that's really stiff initially, and then at some point, maybe at some particular deflection, it gets soft. It stops fighting you as hard, and then the gust can take the wing out of the way. And that's what this is. This is a very simple mechanical concept. Again, it's 100% about geometry, and it's and it's something that came first and foremost through Lego, which makes it particularly close to my heart. So you can see on that video in the upper right the basic concept and how it works. And you can also see it in geometry of the schematics here. What we do is we create torsional stiffness by having a linear stiffness spring at some particular distance from an axis that's rotating, right? So you have a force, you have a moment arm, that's torque. The trick is that the moment arm, which is this bit here in the middle, as it rotates around, the tendon that's connecting your spring to that arm gets closer and closer and closer to the rotation axis, so that moment arm in your equation of torque equals force times moment arm gets smaller and smaller and smaller until this special thing happens, which you can see in the picture in the middle and of course also in the video, where the tendon actually hits. It contacts the pin that you're spinning around. And the trick there, without going into too much detail, is that you then end up with a constant moment arm. So even, which by the way is also very small. So even when the force gets really large, because you've stretched that spring a lot, the actual torque that comes from it is really small. So that's my best attempt to explain that concept quickly. it's probably more useful just to kind of show you how it works and where we got to with it. So the movie in the bottom middle is the working part of a wind tunnel model that I made from, actually I didn't make it, again the student made it, a fourth year student, that made around this concept. And it kind of worked. So you can see the actual wing on the bottom left. I should have brought that up, actually. That's in my office still. And we just put it in the wind tunnel with and without the device, did a direct comparison. And okay, we're cheating a little bit, but we got a 20% drag reduction directly from having this device. Just from the fact that that device was able to push the wing down more when it wasn't being, when it wasn't in normal flight, but get out of the way when a gust hits. Now the cheat, as I mentioned a second ago, is that if you look at this wing, it's a very low aspect ratio wing. So there's a lot of really complex 3D flow going on here, and as a result, we get more of a benefit from this device than we probably get in real life. So I don't think we'll see that 20% drag reduction, which by the way is on the entire wing, in a full-size device, but it's a pretty promising initial result to chase up. Okay, so now we transition to kind of where I'm at with my fellowship right now. So for the last 5 years, I've been on an EPSRC Early Career Fellowship called ADAPS. That's another over-engineered acronym for Adaptive Aerostructures for Power and Transportation Sustainability. I even made a logo for this that no one's ever looked at. But without belaboring the point, there's a little bit of, back to my earlier story, about not quite a crisis in confidence, but starting to question of things. So the work I've been doing for a very long time on morphine adaptive structures, unfortunately, is still actually really far away from reality, right? For lots of reasons, one of which is just the incredible and well-deserved conservatism of commercial aircraft. You can't just throw stuff up there, especially if you're talking about wacky stuff that's flexible, that has elastomer-based skins, et cetera. And so unfortunately for me, it feels like real impact is quite far away still. And as a result, I've tried to find a version of this problem that I think maybe has more potential impact, that has more fundamental depth to it, or maybe just that is interesting and different, I don't know. And the version of that I found is something that I call biologically inspired robotic birds, so bird. And the idea here is, okay, the simple version of the idea is let's just make some drones that look cool and look like birds. The overly philosophized version is how do we figure out how to get better at designing complex systems that have a lot of different things going on at the same time, right, like a bird, where they have control and sensing and actuation, aerodynamics, and structures and propulsion that happen in an unbelievably cohesive way, right? It's sort of everything going on all at once in a way that is just so fundamentally different from how we build our airplanes today. And so I'm trying to find actually real research to do around that, and I've started playing around a little bit with trying to make things that look more like bird wings that hopefully we can design in a more cohesive and integrated way. And the pretty picture version of which are a few things I want to show you quickly around, in the first instance, wings and bones, and then secondly, feathers. So on the wing side of things, we've done some work. I've had a couple really nice postdocs on my fellowship that have looked at the aerodynamic performance of explicitly bird-inspired wing planforms, where we directly copy the skeletal structure of a bird. So, which, by the way, is exactly the same as ours, except their hands are kind of weird if you look at them. That same exact sort of effectively 4-bar mechanism that allows for them to both change the span and the sweep of their wings in flight. I had an RA that made an aerodynamic model around that, where we would map real-life chord distributions from actual seagulls, actual bird-inspired airfoils, map them onto a skeleton that moves like a bird, and look at what we can achieve with that in terms of aerodynamic performance. The short version of which you can see in the plot on the upper right, where we're looking at, in this case, different bird-inspired wing geometries that have been optimized for the two competing objectives of wanting to be able to fly fast, but also wanting to be able to fly very far. So this is what we call a Pareto frontier. We have on the x-axis, we would like to be able to go fast, so we want to be all the way over on the right. And on the y-axis, we would love to be able to fly really far, so we want to be as far up on that plot. So really, we want to be in the upper right corner. But because it's really hard to go faster without making it harder to go further, these two objectives are what we call in competition. They're competing objectives. We end up with this sort of frontier where we can't quite get to that corner, but we can kind of travel along, trading off one objective for the other. So the fun thing that came out of this is that actually the results are incredibly reasonable. So if we allow this bird wing to be whatever shape and size it wants to be, we allow it to be in whatever deformed state it wants to be, we see a very clear trade-off between the designs that are good for flying long range, so in this case you can see a very outstretched long span, versus those that are good at flying fast, where we tuck the wing in and look more like a bird in high-speed flight. So that was a really nice initial sort of mapping out. There's a lot more work to do on that, so I'm going to have to write some more proposals, get some more money. But another thing that's come out of this is, okay, if we want to build these wings around something that looks like a bird skeleton, well, how are we going to make those skeletons, right? And this is where we start to transition into the second half of the talk, because what we've done here is make those bones out of trusses, little tiny carbon fiber trusses. So here's a nice little example. Super light. And the thing to mention here, this is like a nice, this work is still ongoing, but one interesting initial result that already gets me thinking is here. So if we build these bird wings and then we put them on a testing machine to see how stiff they are out of plane, so how good they are at resisting the aerodynamic loads that they have to carry all day long, there's an interesting thing that happens where as you deform to different span lengths, as you shrink or extend, the stiffness that results has actually a really complex response. So initially, you have a very fast drop-off in stiffness because your structure is getting longer and longer. And length is an incredibly powerful influence on stiffness. But when you get to a certain point, it bottoms out and then actually goes back up. And that's really quite unusual. That's a weird thing to see. And in this case, it's really quite intuitive when you look at it. The orientation of the bones relative to the loading direction is also changing as you're changing that span. And you have this, again, a competition of different physics at play, where the larger length leads to lower stiffness, but the increase in alignment between the bone and the load gives you an increase in stiffness. And this sort of behavior is intrinsic to the geometry. So, it'll be in the birds. Now that's interesting in its own right, from maybe sort of like an academic standpoint. The really fun thing that will hopefully cascade over time from this is how can we exploit that? How can we make a structure that is softer in a way that allows it to be better performing aerodynamically, at certain spans versus others. We're now starting to look at, with the same researcher, what happens with torsional stiffness in the same way. When we try to twist the wing, how does that change with span? I expect we'll get a similar, interesting, complex result. And so that is just an initial thumbnail sketch of what, to me can grow out to be really quite a nice, interesting, complex consideration of the sort of kinematic coupling that's happening just all the time in bird wings. And I think there's something quite there, interesting there to dig into. Now, the sort of second bit of work that we've been doing on bird has to do with feathers. And I 100% could have spent this entire lecture talking about this one feather. The first year students I teach have seen me do that for the last few years. Because only maybe 3 or 4 years ago did I come across a paper that talks about how unbelievably sophisticated and beautiful the structure and the materials and the use of materials within the structure of feathers. It's one of the most incredible things I've ever dug into. So I'll have to stop myself. I will just briefly say, as a fun little teaser, that the design of the feather ends up being unbelievably close to the highly optimized design of wind turbine blades. And the first thing to say is that feathers are actually a composite material. There is a series of keratin fibers that exist inside of this feather, embedded inside of a keratin matrix. It's a composite material with two different forms of the same material, which is already really cool. But secondly, that material has a layup. In exactly the same way that we do composites here at University of Bristol, where we stack plies in different orientations to create particular distributions of stiffnesses, the birds have been doing for 150 million years. And the ridiculous thing, and it's probably not showing up terribly well for you guys, but if you look at the variation in that layup along the length of what we might call the spar of the feather, but biologists call the rachis, the central sort of load-carrying part of the feather, the layup has a distribution of 0-degree plies, 90-degree plies, and plus or minus 45-degree plies that looks a whole lot like the wind turbine blades that are all over the world. And that just blew my mind. So I'll stop myself because I could do at least another hour on that. But so what do we do with that, right? That's a beautiful thing to look at, but how does that get us to anything useful for us? Well, in the first instance, we're sort of asking the question, can we just copy that? Can we find a way to make a feather analog that has maybe some interesting related properties? And so we've been doing a bit of that. We've been 3D printing multi-material feathers, super thin, carbon fiber reinforced. We've been kind of putting those together into little, what could be a morphine skin for a little UAV with feather analogs. And again, this is all very early work, but watch this space, I guess, is mostly what I can say. Okay, now I'll speed up a little bit because I do have a tendency to keep yapping on. And we'll switch gears. So now we're going to talk about the wrapped toe reinforced truss technology, Raptor Truss. I invented this in 2009, believe it or not. Never felt more old. I was on a project at the University of Maryland to build a human-powered helicopter. It was a complete waste of time. We spent like 5 years, hundreds of thousands of dollars, like 50 people working on it. And we made a human-powered helicopter completely useless. It was the size of a US basketball stadium. It could sort of fly up and then come back down. Completely useless as a piece of technology, but an incredibly difficult engineering problem that ended up being a really nice sort of motivation or just opportunity really to develop a new piece of technology. So at the very start of my involvement on the project, I was given the job of blade design, so I was in charge of the aerodynamic and structural design of the blades. I spent a lot of time looking around at structures and materials to make the spar, kept running into sort of excessive weight and issues with that, so I came up with a truss as an incredibly efficient geometry solution, again, back to geometry, made from composite materials, which of course are the best materials that we know how to make at this point in time. And combined together with one extra critical bit, which is actually how you make the thing. Traditionally, trusses are a whole bunch of pieces that somebody has to spend a whole lot of time assembling together. They're very expensive. What we came up with instead, you can see on the bottom right, is a continuous winding process. So we take continuous carbon fiber tow, basically thread, we wet it out with an epoxy resin, and we wind it around a mandrel that's spinning, where on that mandrel you have carbon fiber tubes that we just buy. They're protrusions. They're very cheap. We buy them off the shelf. We put, in this case, 3 of those on a mandrel that spins around, and we make a truss. That's my version of on the upper right, that's my version of the collar triangle, where we have our 3 tubes connected together. But basically, the point is that you end up with, I would argue, especially in all the proposals I write, the best of everything. So you have the best geometry that we've come up with as engineers for efficiency. You have the best materials, and we're doing it in a way that's sort of low cost and scalable. Now, that's the basic idea. There's been quite a few students and quite a bit of research over the years, so I'll just sort of briefly overview. We've done this in a lot of different materials, so carbon fiber to start, but we've also looked at fiberglass, I did some work with Vestas, where their products are fiberglass. It's a lot cheaper, so they were curious what we could do there. We've done all sorts of different sizes and shape, tapered, square, triangle. We even got sort of hexagonal trusses we made. I'll draw your attention to the figure in the middle top, which is a really nice result from a PhD student who graduated not too long ago, where he did a very thorough, direct comparison between what you can achieve with a Raptor truss versus what you can achieve with a highly optimized standard carbon fiber tube as a structure. And he did this optimization comparison over a very wide range of applied loads, making sure that those structures were strong enough, and he did it over a wide range of lengths of that truss. And what you see in this figure is how much mass you can cut out by using the truss instead of the tube. And I'll draw your attention to the fact that those numbers get pretty big. So in this case, we look at different lengths. So as you go across the figure, the truss is getting longer. We look at different amounts of applied load, which are very real numbers, right? 100 kilonewtons, 1,000 kilonewtons. That's a lot of force. But you can see that we're actually able to achieve really quite significant reductions in mass, whatever you want really from this plot, but 20, 40, 60% or more because of geometry, right? That's it. That's the only trick. It's just geometry. And personally, I think that's pretty exciting. Another little fun thing to show you while we're here, I showed you already the standard version. Is there a question?
Yeah. When your student was comparing the cylinder versus the truss, was the diameter the same?
No, absolutely not. So we allowed each to be, there was constraints on all variables, including size, but we let each structure optimize to whatever worked best for it. So we were trying to get as open of a playing field as possible. But so look at this crazy thing on the bottom. So I showed you before the standard way of making Raptor trusses, where we spin the mandrel and then go back and forth with the filament. I had a student who looked at the exact opposite, inverted process, where the machine spins around the mandrel, which goes through the machine. And we call this trustrusion. And it's not just, it's not just fun because it's the opposite. It's actually potentially much more useful. So because we've inverted the process, all we have to do is feed in those carbon fiber tubes to the top of this machine, and it sort of spits out truss all day long in a way that allows it to go from being a fixed length batch process where you make one and then you make another one to something that's much more continuous, where you can make much longer lengths, where you can make them at a higher speed and for lower cost. So trustrusion, because it's something like pultrusion or extrusion, and we see this as a really powerful way forward to commercialize the technology. Excuse me. Okay, so those are Raptor trusses as beams, right? As like a truss element. But there's not too many things in the world that are just a single beam, right? Most things are built up into more complex structures. So we would call that a frame in this case. So every building basically that's built these days is built from steel and concrete in frames. And the basic idea here, the question we're asking, is that if Raptor trusses are unbelievably efficient as a beam structure, what happens if you make a larger truss frame from trusses, right? So we call these hierarchical space frames because the overall frame is itself made from trusses. So you could call it a truss of trusses. That's kind of a more fun way to say it. And it's important to note that that's not actually new. And in fact, the concept was baked into the very original project that the Raptor was developed for. So the Gamera human-powered helicopter, the arms, the 4 truss arms that supported the 4 rotors of the helicopter were all made from trusses. So we did this already, but the question is, does this work on a broader scale? And so we've done some work. We've got a lot more to do, but we've done some initial work on trying to quantify the benefits of this. So I alluded a few minutes ago to a project with Vestas. So we did some work with them looking at fiberglass trusses, so things that look like this, where in this case we were focused on what can we do with the shear web, that internal reinforcing web that they build into their wind turbine blades, which at the moment are made from balsa and fiberglass as a normal sort of laminate. if we replace that with a built-up space frame, truss of trusses, what can we get out of it? Now, it's a little bit of a, let's say, swings and roundabouts, because the actual initial estimates of weight savings were really good. So when we looked at this exact structure you see in the picture, we saw that it could do a 50% reduction in mass compared to what they're doing now. But the roundabout is that that wasn't a full representation of the problem, because we hadn't really tackled the question, we hadn't tackled in depth the question of how you connect those trusses together. Right? The joints, which are important in any frame, are definitely important when you're connecting together, more complex truss structures. So that project actually ended because we didn't really have the answer yet for how we were going to do the joints. Now, happily, I've had some researchers in the interim that have really started to tackle this problem in anger. And there's two cool things to show. So the quicker one to show is on the bottom right, where we have a topology optimized structure, which in this case is 3D printed out of titanium, which makes it super expensive, but really cool, as a way to connect these structures together to carry all the loads in between. So that's nice. That kind of is more in line with like a lot of research going on topology optimization. It's just a nice self-contained project, but I don't see that scaling. It's actually really quite heavy, first of all, never mind the fact that it's super expensive. So for me, the more obvious answer is just to do the same thing that we're already doing, but in 3 dimensions. So instead of a sort of 2D, linear winding, what if we start winding more complex 3-dimensional structures, right, that are able to connect together 3 trusses in this case, 4 trusses in this case, 2 trusses in this case, with, again, a really highly optimized geometry where you're directly connecting the points, you've got the fibers aligned with the load, you're getting all that advantage of truss structures and frames. And this has worked out pretty well. I'll very briefly say there was definitely a rabbit hole here that we did not see when we started this project, which meant that the poor PhD student had a very different project than they thought they were going to have. But what we really have here, in addition to a manufacturing technology for a truss structure, is a graph theory problem. We have a traveling salesman problem, where we need to figure out when we make this thing in what order to wind, where to go from node to node, and how to ensure that we can actually create the entire structure in one continuous winding. And I won't say too more about that, except that it ended up being this whole thing that poor Kyle had to spend a couple years coming to grips with. But he did an absolutely fantastic job on it. He's come up with a really nice piece of code that automates that process of simulating the winding. Okay, so another, what about question? So, again, trusses as beams are already a decent place to start. There's lots of beams. Trusses of trusses as frames for general structures. Okay, now it's starting to feel more real. But of course, a lot of things in the real world aren't, giant, open, porous structures, right? Well, there's a lot of things that need to have skin, right? They need to have continuous outer surfaces. So, very obvious examples of airplanes and rockets. These structures are made with skins that today are, very often things like sandwich panels, where you take advantage of some of the stuff I was talking about earlier with the gator panels. But we had the question or the idea of replacing our traditional way of doing this, stringers, sandwich, etc., with just Raptor trusses, right? We start with the assumption that Raptor trusses are always a good idea. So I had a PhD student on this who's looked at reinforcing standard, composite carbon fiber layup skins with these trusses. Early on, he did a nice initial low fidelity analysis to see if this was worth doing. And I'll spend a couple seconds to walk you through this. There's a lot going on. But the basic question we're asking with this figure in the middle is how much better than a best possible answer for a traditional sandwich panel can we get if we replace that with Raptor trusses? And the answer is pretty good, I would say. So what this figure is showing is a single point, the blue diamond on the sort of bottom left. That is an actual Raptor shell that was made and tested experimentally. So those are real numbers. We're comparing the real numbers for the mass and the displacement, which is basically the stiffness, of that panel against hypothetical best achievable answers for sandwich panels. And in this case, a couple of key numbers to point out that the sandwich panel only gets close if it can be really, really thick. So a super lightweight core and like, a couple super thin face sheets really far away. That's the only chance it has of getting to the same level of stiffness. But even still, so if we take, again, this is a Pareto frontier, so we've got mass and displacement. We want low mass and low displacement. So we would like to be in that corner. We can never get there because these things are competing, so we end up once again with the frontier. But if you look at the blue diamond, the closest points on the frontier of what's achievable with sandwich panels is either 50% heavier, or I think it's an 80% increase in displacement. And it's actually even worse if you force that sandwich panel to only be as thick as the Raptor shell. Because again, it was cheating, it was trying to be as big as possible. If you make it so it can't be any thicker, then it's 10 times better in terms of achievable performance. So again, the geometry here is very powerful. There's a lot here that we could chew on. If we can, of course, if we can make the structures in a way that works in the real world. Another sort of passing note, we can do this curved as well. So I had a nice third-year project student very recently who made a curved version of a Raptor shell. There's a lot of curves on airplanes, so that feels important. And then, as my final topic, you'll be happy to hear after me rambling on for some time now, is on that final step that I alluded to in the very beginning about how can we get back to a more natural approach? How can we use the geometry of Raptor trusses in this case to compensate for nature and what it can provide us in terms of materials? And so for this, we just want to make natural versions of Raptor trusses. So there's a PhD student working on this now, Matt, and he's making Raptor trusses with bamboo, where we actually use bamboo in its native form as a culm. It's called the stalk of the bamboo. We keep that. That geometry is also really, really good. It's up there with the feather in terms of sophistication. Again, I could spend an hour telling you about how unbelievably evolutionarily optimized bamboo is. Let's just take that for a given for the moment. We're also using a natural fiber for the windings. So in this case, we have flax fibers. And the epoxy is a hard part. Epoxy is a petroleum product. This particular one is partially bio-based. So it has, I think, about 30% of its content actually comes from tree sap. That's been modified to have exactly the same chemistry as epoxy. And so it has a very similar performance. So yeah, the first thing is, can you do this at all? It's looking fairly promising. So yeah, let's use that geometry to make up for that genuinely quite significant deficit in the strength of the natural materials, in their elastic modulus, and their mechanical properties. But that's not really enough, because there's a couple other things that go on. And the biggest issue is that natural materials are incredibly variable, right? Their properties, their geometry are unbelievably dependent on literally every single thing that happens to them, from when they start growing. So climate, soil, the seasonal variations, the moisture uptake, they're all over the shop. So we have this other deeper problem around compensating or adapting what we build to that variation. And at the moment, we're taking two very different but coinciding approaches to handling variability. And the first is perhaps the more obvious. So we just want to measure what's there, and then we'll see how we can adapt our process to compensate for what the variation is intrinsically. So there's a few different ways of doing that, but the simple way to talk about it is just, again, the culm, that stick of bamboo. So in this case, the student has made a very simple, very fast geometry scanner. We run that culm through a series of displacement measurements that actually sort of then measure the outside shape. And you can import that as a three-dimensional representation of the actual culm. He can then actually build a finite element model that represents that with its actual geometry. and we can run that analysis, we can compare it to experiment, and you'll see on the bottom in the middle, okay, that actually works okay. We're getting pretty good agreement already, just by measuring what's there and then bringing that into our process. But that's a little bit of like the low-hanging fruit. And the thing I'm super excited about in particular, which is very recent, is the idea of not just dealing with what's there, but also not going to the other end of the spectrum and destroying what's there, right? So probably should have mentioned earlier that most of the things that we have in our, in the world that are made from bamboo have been made with a very deconstructive approach, right? So very large culms of bamboo are grown, they're split down into tiny little slivers, and then you glue back all those slivers to make a chopping board or cell phone case or whatever. And that's better than not using bamboo, but there's a lot of resin in that, and of course, unfortunately at the moment, that's mostly a petroleum product. And so not only is it cutting into your inherent sustainability, you've also completely destroyed that unbelievably beautiful architecture, right, that nature's given us in the calm. What a waste. Why throw out the coolest part of it just to get some fibers, right? So that's how we do it now. And I told you a couple examples of a non-invasive way that we can sort of respond to what's there. But what I'm really interested in is there something in the middle where we can change the geometry, where we really, really need to have precise geometry, but let that bamboo be its beautiful, evolved self everywhere else. And that's what I have here. You can probably see it better in the picture on the bottom right. And we're working on a new thermoforming process that allows us, in a very simple, clean, fast operation, to take the end, in this case, of the bamboo, which is definitely not a circle and very inconsistent in its dimensions, and we thermoform it into a perfect cylinder. Now, I can't take too much credit because this is sort of my reinterpretation of steam bending, which, if you know anything about woodworking, is an unbelievable, thousands of year old process for how we can change the shape of wood in a way to make it useful for building ships, etc. So this is effectively a form of steam bending. But the trick is that if we do this at the end of our bamboo truss, well, okay, it's a little bit weird and messy here, but we can compensate for that. We can predict what's going to happen. But when it's time to connect this truss to other trusses or to anything else, we have a very precise, very nicely controlled interface, right? We've changed the geometry, but only where we need to, and in a way that keeps as much as possible of what's already good. And that, to me, I think is the perfect place to end, because that feels like I'm getting to maybe where I want it to be, right? Where we can get the best out of what we have, by cheating with geometry and being as clever as we can, without relying on sort of over-engineered approaches. I do have to, I have to apologize a little bit. So in 2019, we did an outreach at the Green Man Festival in Wales, which is a really nice festival to do. For that, along with one of my postdocs, Ian, I made sort of the first natural material Raptor truss thing, which was this airplane. Little did I know that as part of an advertising campaign, it would become this slightly cringy thing in the Bristol airport, if you've been there. Anytime in the last 3 years, these posters have been going around. And actually, just last week, one of the other professors here said that it's not even just the little digital posters anymore. They've made like this big printout when you come in back. So obviously I'm bragging, but it's a little bit ridiculous. So yeah, let me wrap up. I just have 3 more things to say as a sort of where I see where we're at and I don't know, maybe what I'm trying to do. And my vision, right, for a more sustainable future in picture form, a sort of hopefully brighter sky ahead. I just want to really hammer home for the 17th time that I believe that geometry is an unbelievably powerful tool that we have as engineers that, frankly, we don't talk about enough. It's kind of baked in everything we do, but we don't think about it necessarily as exploiting geometry. So please, exploit geometry. I hope as well to maybe have gotten the point across that sustainability in structural engineering is something worth spending our times on. And then just to bring it back to that 5th grade geometry teacher with another one of his gems, and to close us out again on Arthur Koller with his beautiful aeroelastic triangle. The best angle to any problem is the triangle. Okay, and that's all I've been trying to do in these last many years of my career. Just because that was too light and cheery of a note to end on, and this is actually a little treat for Mark, because we both love Tom Waits, who's a very oddball but incredible musician, and he's got a song where he says that the earth died screaming while I lay dreaming, and I have to say, having been in academia for quite some time, that's a lot of what we do as academics, is we kind of have our little dream worlds. And I'm slagging myself off at the same time, so I'm allowed to do it, but I don't know, maybe we can shift our focus a little bit and try to do less work. That's it. Thank you all very much.